Okay, so let's look at an example of finding the total transconductance and total resistance for a circuit that we want to analyze. And let's do this for the case of, say, using this as a common emitter amplifier. And what a common emitter amplifier means is we're going to take the input on the base and the output on the collector. So what we're looking for here ultimately is the voltage at the collector due to a voltage at the base. And that's going to be the product of GM times RT. So what we're doing, what we're going to do for finding GM is we're going to go to the output terminal, which is the collector terminal. And notice that I've labeled the external resistor R cent sign to distinguish it from the collector resistance looking into the transistor. What we're going to do here is we're going to short circuit the output, and we're going to find the current I out that flows into that short circuit due to a voltage input at the base of the transistor. We can figure out what to do with the other external circuitry later on. Namely, it's probably just going to cause a voltage division, and we can solve for that later. So when finding the transconductance, we put this test current, test voltage in, measure the current that flows into the short circuit, and we would do that with KCL analysis at this node and this node. What we would find every time that we do this analysis is that GM is equal to minus little gm divided by 1 plus little gm times RE. This is the general case. If RE goes to 0, then big GM is just equal to little gm. We will solve an example of this in our homework, so I will leave it to you to do the algebraic manipulations in KCL at each of the nodes. Now, to find the total resistance at that node, we would plug in a test voltage source. We'll call it Vx. And we'd measure the current that flows from that test voltage source, such that RT was equal to Vx over Ix. And if we did this, what we would find is that the resistance would always be equal to the resistance looking into the collector in parallel with the resistance externally that's tied to the collector. So we could move this operation by placing the test voltage source just to the left of big RC and figure out what R little c is equal to. This will take a standard form, and we'll of course find this in the homework as well. And what we would find is that RC here, R little c, is always equal to R out of the transistor times 1 plus GM times RE of the transistor. So what we really see is going on with a voltage amplifier is that the transistor first turns an input voltage into an output current. That output current flows through a total output resistance that converts the current back to a voltage. Now we'll, in the next set of slides, write out a generalized expression for each type of amplifier that exists: common emitter, common base, common collector for the BJT cases, and common source, common gate, and common drain for the MOSFET cases.